In the previous video, we started talking about the Smirnov transform for sampling from real valued random variables. And we looked at this special case of when the CDF was invertible. But we noticed that oftentimes the CDF is not going to be invertible in cases of interest, like this one was if x is exponentially distributed with some parameter, then its CDF, this part is nice, but then it's less, it's equal to 0 over here. So strictly speaking, it's not invertible. And here, for a discrete type of random variable, the CDF has these steps, and it's flat, it's constant on each of these regions here, so it's not invertible. So this would be like if x is Bernoulli, say, I don't know, 4/10 or something, looks like. And so now we're going to take a look at a more general case of the Smirnov transform. So this will be the general case. Now let f be a CDF just to the closed interval. So before we were going to the open interval, and now we're allowing it to go to the whole closed interval. And f is a CDF. And we'll define some function here, this function g, from the open interval to the real numbers. And we define it by the following. G of a, for some number a in that interval, is the infimum of all the real numbers, of the set of all the real numbers x, such that a is less or equal to f of x. So in other words, the infimum, you can think about it heuristically as sort of the min of this set. But there are cases in which the min does not exist and the infimum does. So a more general, type of min is what's called the infimum, and it's the greatest lower bound. It's the largest number that's less or equal to every number in this set. Largest real number. And now, if u is uniform on the interval from 0 to 1, just like before, then g of u, the random variable g of u, has CDF f. So g of u is distributed according to this CDF f. So here you can see that g of u sort of plays the role that f inverse did in the previous, the previous special case. And in fact, so here's a few remarks. A first remark is that in fact, if f is invertible, if it goes to this open interval from 0 to 1, and it's invertible, then g equals f inverse. So this is indeed a generalization of the previous special case. Invertible. Another thing here, which is important, is that here I said that g was going from this open interval to r, real numbers, but this infimum, we need to guarantee that this actually is a real number. It could be infinite or it could be minus infinity. And so it turns out that it is a real number, and the reason is because f is a CDF, so f of x it converges to 1 as x goes to infinity, and it converges to 0 as x goes to minus infinity. So that's a technical point that you can check. So g of a is indeed in this interval, since f of x goes to 1 as x goes to infinity, and f of x goes to 0 as x goes to minus infinity. So for the case of when a is say near 1, you need to ensure that this is a non-empty set to ensure that the infimum is not infinite, and that turns out to be the case because of this. and similarly symmetrically for the other case, you can ensure that it's not negative infinity. There's not a sequence of x's going to minus infinity for any fixed a. And let me make one more remark here, which is that something which is a bit strange about this is that I haven't actually seen this proposition presented in this general of a way. Usually people say that f must be continuous. F continuous. And I mean, the references I've checked all require f to be continuous, but I don't see anything wrong with the proof that I'm about to give you. So I'm going to give you a careful proof of this, but I wanted to make this little disclaimer here, this little remark, just to let you know that basically the references I've checked all say that f should be continuous. And if you see something wrong with this proof, by all means, pay close attention and let me know if you see an issue, and I'll make an adjustment to this video. Okay, so here's the proof that I have come up with for this. So the proof involves first a little claim. And the claim is that for any a in this interval, try to be a little clearer, interval from 0 to 1, and for any real number y, we have the following. We have that a is less or equal to f of y if and only if g of a is less or equal to y. So this plays the role in the invertible case. Remember, we had this, well, it was also the purple property here, that we had this, that a was less or equal to f of x if and only if f inverse of a was less or equal to x. And down here, this is the same, just a perfectly analogous property. G is playing the role of f inverse here. And let's prove this little claim. Let's prove this. So first let's prove this implication. And to do that, we start out by assuming a is less or equal to f of y. And so then we want to prove this, so let's write out what g of a is. It's this infimum of this. Remember, it's this thing, this infimum over all real numbers x, such that a is less or equal to f of x. And we'd like to say this is less or equal to y. So this is very simple, because it turns out that y is actually a member of this set. Y is in this set because a is less or equal to f of y by assumption. So y is in this set, and therefore the infimum over all the elements of that set must be less or equal to y. And so we have this. So we have this is less or equal to y. And that's exactly what we wanted to prove. So now we need to prove the other direction. So we suppose that g of a is less or equal to y. And we'd like to prove this. So this one's a little this one's a little more subtle. If g of a is less or equal to y, so we have this infimum, and for the same reason that this second remark holds, this set is always non-empty. So you can check that's true because of this second, for the same reasons as the second remark. And because it's non-empty, there exists a sequence of points. So then there exists a sequence of points in that set. Let's call them x1, x2, x3, and so on. And all of them are greater or equal to g of a, because that's the infimum. And they converge. So it's an infimizing set. These points converge to g of a. And furthermore, because they're points in this set, then they all satisfy this property. So a is less or equal to f of xn for all n. So the definition of the infimum and the fact that the set is empty, is non-empty, guarantees that we can choose such a sequence. And now, so this implies, so we have this property, and let's take the limit. If we take the limit as n goes to infinity, well, the left side, of course, doesn't depend on n, so this is the limit, and f is a right continuous function. So remember, these x's are converging here, they're converging to g of a. So since f is a right continuous function, these are all greater or equal to g of a, and they're converging to g of a, then this limit equals f of g of a. F is a right continuous function because it's a CDF, and every CDF is right continuous. G of a, so f of g of a, and now by assumption g of a is less or equal to y, and f is non-decreasing as a CDF, so therefore f of g of a is less or equal to f of y. And that's exactly what we wanted to prove. A is less or equal to f of y. So that proves the little claim here. And now we have exactly the property that we need. It plays exactly the analogous role to as in the invertible case. And so let's see why that is. So now the probability that g of u is less or equal to y, this is the CDF of g of u, this equals the probability that u is less or equal to f of y, because we have this property, u is less or equal to f of y, if and only if g of u is less or equal to y. So that's over here. So these probabilities are equal. And then just like before, this is the CDF of u evaluated at f of y. So let's, if we called that h before, let's call it h again. The CDF of u evaluated at f of y, and f of y is always in the interval from, well, the closed interval from 0 to 1, and so this CDF evaluated at that point is just the point, so it's just f of y. And therefore, the CDF of g of u is f, and so g of u is distributed according to the CDF f. And that proves the proposition. So I wanted to go through this in detail in order to explain, to really, because like I mentioned in the previous video, I've seen some proofs of this, actually not in this generality, but some proofs of this Smirnov transform that were not actually completely correct, and also some statements of it that were not really completely clear or correct. And so I really wanted to go through this in detail and explain and do a thorough proof. All right, so that's the general form of the Smirnov transform. And next we're going to take a look at some examples, or at least one example, of actually how to apply this. And we'll look at a sort of more simpler case. I think I'll do the exponential random variable. That's a nice easy one to sort of work out. All right, so we'll come back and we'll do that next. We'll see how to apply this.